our last section has us graphing two variable inequalities, and basically that's just us graphing lines and then shading one side of the line. I'm going to really kind of focus on what this represents and why we include the shading, but just a couple kind of quick things about when we're graphing lines of inequalities. The first thing that we need to decide is our line going to be a solid line or a dashed line? So we use a solid line when we have greater than or equal to or less than or equal to. And the reason that we use a solid line is because we're saying the points on the line will make the inequality true. Okay, so solid line for greater than or equal to or less than or equal to, as opposed to a dashed line, which is just less than or just greater than. Okay, so when we use that dashed line, we're saying the points on these lines do not make the inequality true. And I'll explain what I mean by that here in just a moment, about making the inequality true or not. So looking at A, this is going to be a dashed line because of this being just greater than, as opposed to B, this will be a solid line because we have the less than or equal to. And from here, we'll graph a line just like we normally would. So when you're graphing lines, the first thing you want to do is recognize what kind of form is this line in. Okay, if we don't know, that's something that should be studied using that remediation packet that we worked on Friday. But both of these lines that are the same equation, these are in mx plus b. So our first point is to graph the y-intercept, which is at -1. So I'm going to go on the y-axis, put a dot at -1. Now I'm noticing my slope is positive. So my line should be sloped so that it's going up to the right, okay, in both cases. And my slope is 3, telling me to go up 3 and then to the right 1. And by going up and to the right, that's how I'm getting that positive slope line. In this case, we'll go ahead and let this graph span the entire, as much of the graph as possible. And then this one's going to be dashed. And it's going to happen where, especially, ideally we should be using pencil, but I know sometimes we might only have a pen or a marker next to us. If you accidentally draw a solid line, just make a note to me that say this is dashed. Okay, that's absolutely okay. And then for the other one, I just need to use my same slope. So up 3, right 1. And then we're going to make that a solid line, so just like we normally would. Okay, so step 1, graph a line. Okay, and the only really thing we need to think about is a dashed line or a solid line. Now we got to figure out where to shade. The shading is really dependent on if we have y being greater than the right side of the equation or y being less than. But another kind of just good thing to do is to test points, and this really gets into the shading. So what I mean by test points is let's pick a point anywhere on the graph, and ideally anywhere on the graph that is not part of the line. So I'm going to use, let's use 2, -2. So 2, -2. And what we're going to figure out is, does this point or does this combination of x and y make this inequality true? So I'm going to plug x and y into the inequality. So -2 is greater than 3 times 2 minus 1. So -2 is greater than 6 minus 1. And so I get -2 is greater than 5. Is that a true statement or a false statement? -2 is greater than 5. That's very false, right? -2 is not greater than -5. And since this is false, that tells us that this particular point or this combination of x and y does not make the inequality true. And thus, every point that is on this same side of the line will give us a similar result, something that is false. So what we're going to conclude is, if this side makes the inequality false, the other side will make those points true. And so we shade the side that includes all the points that make the inequality true. So if you pick any point in that shaded region and you plug in the corresponding x and the corresponding y, it will always result in a true statement. Now, another thing, and some of you have done this before, is when I read this inequality, this says y is greater than. Another way to figure out shading is if y is greater than our equation, we're going to shade above the line. So if I just pick a point and draw an arrow above the line, that is telling me where to shade. So you don't even need to test points. Okay, testing points will always confirm that you're shading correctly. But again, greater than, above the line, less than, below the line. Okay, sometimes it can be hard to distinguish above and below depending on the slope of the line. Which is why I would always recommend just plugging something in, but it doesn't matter. Okay, if you want to just say, hey, it's greater than, I'm going to shade above, less than, shade below, fine by me. All right, so the last one, okay, this is less than or equal to, so that means we're going to shade below the line. Okay, and if I were to pick the same point, okay, so let's just pretend that I picked 2, -2 again. Well, we're going to get basically the same result here. -2 is less than 3 times 2 minus 1, where we got that this is -2 is less than or equal to 5. Well, that's a true statement. And since that's true, that means we're shading the side that includes the point that we tested. So the last quick thing I just want to touch on here is the difference between a solid line and the dashed line. The solid line means that the points still make the inequality true. So let's take this point right here, for example, which is 1, 2, and let's see what happens when we plug that back in. So I get 2 is less than or equal to 3 times 1 minus 1. So 2 is less than or equal to 3 minus 1, or 2 is less than or equal to 2. Well, this is still true, right? 2 is not less than 2, but it is equal to. When we say less than or equal to, just one of those things needs to actually be true. And so because this point still gives us a true statement, that's why we're doing a solid line, because we are including those points in what makes the inequality true. Okay, so that is basically two-variable inequalities. Graph the line, shade above or below the line. That's all you got to decide, okay? And how you want to figure out where to shade, giving you a couple ways of how you can decide to do that from here, okay? So I did throw in a quick word problem for us, quick application problem. It says the map shows the number of tickets needed for small or large rides at the fair. You do not want to spend more than $15 on tickets. How many small or large rides can you ride? Well, one thing that I've pushed on us when we see new problems, or especially word problems, okay, what do we know? We're going to list that out. And what do we need? Okay, so we know that we don't want to spend no more than $15. So let's just say we have $15 to spend. Looking at the map, we get a little more information in that tickets are 25 cents. So that's $0.25. Large tickets are large rides. Cost 5 tickets. And small rides are 3 tickets. Okay, so one thing that we need is some kind of equation, or even better, an inequality. The reason that an inequality is better here, because it just says that we want to spend no more than 15. So we want whatever combination of rides that we spend or go on just needs to be less than 15, okay, less than or equal to. So this is, in this case, we're going to use an inequality. So we need an inequality. And one thing that I like for us to do when we're trying to solve or build an equation or an inequality is to define variables. So let's start with the variables. We're going to have an X and a Y. Now, our variables are defined by whatever we're trying to figure out. We're trying to figure out how many small or large rides can we ride. So let's let X equal the number of small rides and Y equal the number of large rides. And so now I've got a bunch of information pulled away from the word problem. Now I'm just going to use this list to go ahead and work on building this inequality. We've defined the variables. So now I'm like, okay, what do I know about each variable? I know that small rides cost 3 tickets. So 3 tickets, 3x, plus the 5 tickets, so 2y. And then I'm like, okay, this whole equation is in terms of tickets, right? One thing we can figure out is how many total tickets can we buy with the money that we have, right? So we also need to figure out how many tickets can we buy. Go ahead, what do you got? It should be 5. Good call. Talking and writing and doing math at the same time can be hard sometimes. That's why when I write, I misspell things all the time. There we go. Good call. 3x plus 5y. So now we need to figure out how many tickets can we buy. We know that if each one is a quarter, that means we can get 4 tickets for $1. So we need to figure out 4 times 15, which is 60. So that means we can get 60 total tickets. So for our inequality, we need the number of tickets that we buy, or that we end up going on rides and spending, to be less than or equal to 60. It's the maximum number of tickets that we can get with the $15. And to me, this will always be the hardest part of any word problem. How can we build that inequality or equation? And now we need to graph this. To graph this, there are a couple different ways. You could go ahead and find the x and y intercepts, or we can just work to get y by itself. And I'm going to do that. So I'm going to subtract 3x, so 5y is less than or equal to negative 3x plus 60. And I'm going to divide by 5. And so we get that y is less than or equal to negative 3/5 x plus 12. And then just a reminder that when you are getting y by itself, if you happen to multiply or divide both sides by negative, we still flip that inequality sign, just like we saw when we were solving inequalities. So now I can graph this. This is an mx plus b. So I'll go to 12. My slope is negative 3/5, but every square is 2, so I'm going to be a little more thoughtful based on the scaling here. So this is telling me to go down 2 and then 3, and then to the right 2, 4, 5. And then down 3 again, so 1, 2, 3, and right 1, 3, 5. Down 3, right. Down 3, right 2, 4, 5. And then one last time, right 1, 4, 5. Since we are allowed, since we have less than or equal to and spend the maximum amount that we have, this is a solid line. And then with this being less than, again, if I just pick a point and draw an arrow below that line, that is the less than side that we will shade. And so what this shading represents is any combination of rides that you can go on at the fair. Okay, so you can do any combination for what we're seeing within the shaded region. If you're wanting to maximize the number of rides you go on, you would want to use the any point on the line. Okay, those would be the maximum number, or that'd be you using all your tickets there. Okay, go ahead and flip this page over. Just got a quick thing with absolute value inequalities, and I'll come around and get you all your homework. All right, so graphing absolute value inequalities, nothing has changed. Just now our graph should be a V-shape, so we'll review what we had learned. That was back on block day. The first thing that is kind of weird about this equation is we don't have y by itself. Let's accomplish that first. So the first thing that I don't like is that I have this 1 minus y, so I'm going to subtract 1 from both sides, making my equation negative y is less than the absolute value of x plus 2 minus 1. The next thing is that the y is negative. We need it to be positive. So I'm going to either multiply or divide the entire equation by a negative 1. So that makes this y. The less than will flip to be greater than. Negative 1 or absolute value divided by negative 1 just makes that whole term negative. And then a negative divided by negative is a positive. Okay, so now we'll identify the vertex, which remember that vertex are our horizontal and vertical shifts. So this is shifting our graph left 2 and up 1. So negative 2, comma 1 is the vertex. The A value is negative 1. Put it over 1, and that's our rise over run. And then remember that the negative is a reflection across the x-axis. So this should be opening down when we go to graph it. So I'm going to go left 2, up 1, and then just down 1 and over 1 in both directions. All right, and then our dashed line and solid line rules are the exact same, with this being just greater than. This is a dashed line, meaning every point on this line does not make the inequality true. And now we just need to figure out where to shade. With the absolute value, you will either shade the outside of the V, okay, so the entire outside here, or the inside. The way you can figure out is the exact same as before, where if it is greater than, pick a point that you plotted, draw an arrow up, that is greater than, that is the side of the V we want to shade. So we want to shade the outside here to represent all the points that make the inequality true. Or we could test a point. How about let's test 2, 2. I'm anticipating that that will give me a true statement because of where I've already thought to shade by getting greater than. And I'm going to plug this back into the original. So 1 minus y is less than, how about 1 minus 2 is less than the absolute value of 2 plus 2. 1 minus 2 is negative 1. 2 plus 2 is 4. And the absolute value of 4 is 4. Well, negative 1 is definitely less than 4. Thus, this is true. And thus, that is confirming the outside of the V contains all the points that make the inequality true. And I don't need your coloring to be perfect. Don't spend too much time making your coloring and shading perfect. Should be quick there. All right, let's do this. Why don't you all write the inequalities based on the graph you're seeing in problem 4. So kind of doing the opposite, writing the equation of the absolute value equation and thinking about the inequality symbol that we want to include for that graph based on the shading and type of line. All right, give you a couple minutes to do that. I'll come around with homework. I really don't need it. All right, and for those of you watching online, you can check your graphs. Each vertex, that is actually left 2, 4, so the x-coordinate's -4. And then it looks like we'll call that being right in between these two lines on the y-axis here. So that's up 2, and then a half makes that 3. So the vertex 2 and -3. For the shading, if you're not sure about the symbol, just like we did when we graphed, come up with a guess. Put greater than or less than, then pick a point in the shaded region and plug it in and see if you get a true or false statement. Right, that is all that I have for you today.